Welcome back to Math Attack!
If you're having a hard time with math,
You've come to the right channel.
my name is Jillian Patricia R.
My name is Ythan Ricci v. Austria.
from
11 Galilei.
And today we're going to talk about
Breakups.
There's a hole in my heart. And I don't think you will be the one who can feel it anymore. Let's break up. You're jumping into conclusions? It's over. I thought our love would be infinite. But it seems like everything has its limits. It's over.
whole,
Jump. Infinite.
These words are not really from breakup lines. In fact, they are very important parts of our topic.
But what we're going to talk about is the different types of
Discontinuity. By the end of this video, you should be able to 1. Illustrate the types of discontinuity and other characteristics.
2. Determine the type of discontinuity by looking at the graph.
And 3. Identify the different types of discontinuity by solving. So, shall we begin?
We shall.
To start off, let us first recall the core topic of this lesson: continuity. What is continuity? It is defined as a state of being continuous, and continuous is characterized to have no break or no interruption. If we apply this in functions, continuity in a function or f of x is said to be continuous at x equals c. If the following conditions are met: first, f of c exists. Second, the limit of f of x as x approaches c exists. And lastly, f of c is equal to the limit of f of x as x approaches c. F of c can be evaluated by plugging in or substituting the value of c into f of x. The limit should be evaluated from the right and left hand side. If these hold true, there is continuity. A function which fails to satisfy all conditions is classified or said to be discontinuous. There are two ways to identify continuity. The first is by looking at the graph, which is often showing holes or hollow circles. The second is by solving, in which you evaluate three conditions. There are three types of discontinuity, which are as follows. First is called removable or whole discontinuity. A function is said to have this kind of discontinuity at x equals c if f of c exists and the limit of f of x as x approaches c exists, but they are not of equal values. The second type is called essential discontinuity. Under this classification is the jump essential discontinuity and an infinite discontinuity. Although they belong to the same category, some books or materials actually separate these two. For jump essential discontinuity, a function is said to have a jump essential discontinuity if f of c exists but the limit of f of x as x approaches c does not exist, or vice versa. So either of the two, D and E, or does not exist. Next, for infinite essential discontinuity, a function is said to have discontinuity at x equals z if x equals c, or f of c, and the limit of f of x as x approaches c does not exist. It is also said to be asymptotic or contains asymptotes. Time to graph. In this first example, you can see that if I trace this line, there will be a point in which the function stops, and there is a hole. It is then a removable type of discontinuity. If we evaluate f of 2 will be equal to 4. If we take the limit, the graph approaches the value of 2 from both sides. As you can see, they are unequal, so it holds true. For the next graph, as I trace the first graph, there is a sudden jump towards the next function. As you can tell, it is a jump essential discontinuity. If we evaluate using the conditions, f of 1 is equals to 2. Next, if we take the limit as x approaches x,
1.
it can be seen that two graphs came from the left and come from the right. So we need to evaluate the two-sided limits. From the left, the limit is equal to 2, and from the right, the limit is equal to negative 1. These two are not equal. Therefore, the limit does not exist, or DNE, making it jump. Lastly, in this example, if we trace the first graph, it approaches positive infinity, and the other one approaches negative infinity. This is then an infinite essential discontinuity. As you can see, the appearance of an asymptote is very evident, making it infinite. Both f of c and the limit of f of x as x approaches c does not exist. If there is no graph given, we evaluate by solving. The first example is a type of piecewise function, x squared plus 6x plus 8 when x is not equal to 4 and 8 when x is equal to 4. Evaluating f of 4, we get 8, since the function already says that it is equal to 8 at 4. The limit of f of x as x approaches the first function since we are approaching 4, so there are values not equal to 4. If we factor this, we get x plus 4 times x plus 2 all over x plus 4. We cancel out the common terms, leaving us with x plus 2 equal to 4 plus 2, which is equal to 6. F of c is not equal to the limit of f of x as x approaches c. Therefore, f is discontinuous at x equals 4, and it has removable discontinuity. Take note, removable functions can be fixed or made continuous. This can be made possible if we redefine, that is, assign the value extracted from the limit of f of x as x approaches c to f of c. In this given, let f of 4 be equal to 6, therefore making it continuous. Next example is the piecewise function 5x plus 1 when x is less than or equal to 2, and 2x plus 3 when x is greater than 2. Again, there are two functions. In solving for f of 2, we make use of the first function since SAS is 2 in the condition. Substitute 2 in the equation, we get 5 times 2 plus 1, which is equals to 10 plus 1, that gives us 11. In solving for the limit, we make use of the left hand and right hand side. The left hand side would use the first one since negative or less than 2 values are of the left. If we evaluate, we get 11. For the right hand side, we use the second function that belongs to the right side due to its positivity. If we evaluate, we get 11.
7.
The sides are not equal, so the limit does not exist. Therefore, f is discontinuous at x equals 2, and it has jump essential discontinuity. For the third example, we have x plus 9 over x squared minus 81 at x equals 9. Evaluating f of 9, we get 9 plus 9, which is 18, and 9 squared is equal to 81. Minus 81, this gives us 18 over 0, which is undefined, so it does not exist. In evaluating the limit, we take two sides. For the left-hand side, all values approach the negative infinity eventually, while the right-hand side will approach the positive infinity. As such, the limit does not exist due to inequality. Therefore, f is discontinuous
At x equals 9.
and it has infinite essential discontinuity.
And that's a wrap.
Thank you for watching our videos. If you want to see more of us, follow us on our social media handles here.
For more tutorials, don't forget to hit that subscribe button, like, and share this video.
Comment down below on what topics you want us to teach next.
And always remember, preparation is the best shield against the attacks of ignorance. Bye!